In this series of lectures on chemical thermodynamics, today I shall try to explain the second law of thermodynamics. Different statements regarding the law, and where there is a limitation of the first law, why the second law is coming, and why the second law becomes necessary. All these things I shall try to discuss today. First law of thermodynamics, let me first discuss the limitation of this first law. We all know now the first law is the conservation of energy. If one form of energy disappears somewhere, then equivalent amount of this another form of energy must reappear. In this conversion of these different forms of energy, actually first law remains silent. Under what condition this conversional process of energy would occur? I may illustrate this limitation by an example. Let us take the one metallic body A, having its temperature TA, and here it is another body, another same metallic body, having the is B, and its temperature is TB, and these two bodies are connected by a conducting metallic wire. Now the first law states that if the heat lost by A, then this amount of heat will be gained by B, an equivalent amount. Say if a Q amount of heat is lost by A, then this amount of heat will be gained by B, or if a B or this Q amount of is lost by B, then that amount of heat will be gained by A. If the heat is not lost by some other processes like a conduction, like the radiation or convection, etc. So, but if this is the process, and this is the heat flow. This is the heat flow process. This process is called heat flow. Heat flow from this body A, between these bodies A and B. And if this is maintained, then first law is satisfied. That means heat is not being lost. Heat is an energy, heat is a form of energy, and heat will not lost by this flow of heat. So if we put some questions under regarding this heat flow, the questions are if we put these questions number 1, whether heat flow occurs or not, whether the heat flow occurs or not, and this is actually feasibility of this process. feasibility of this process. And the second question, if a heat flows, then to what direction? Then what direction heat flow occurs? And this is the direction of the process. And the third question, to what extent heat flow continues, and this is the extent of this process. Extent of this process. For any process, we can put these following questions: whether the process will occur or not, or the feasibility, direction, and extent of this process. And the first law remains silent about this answer of these questions. But the answer of these questions is answers to these questions are available from this statement of the second law of thermodynamics. Means the second law comes to the rescue for these limitations of this first law of thermodynamics. And the simple statement of the second law for these questions is very simple and known to all of us. And the statement is the statement of this second law for this process is that heat flows from high temperature to lower temperature. Very simple. And all of us, we know this sort of statement from our own experience. Actually, this statement can successfully answer the questions I put here. These answers. Now I can give these answers. Answer to this question number 1. If TA is not equal to TB, heat flow occurs. This means this is the feasibility. This is the conditions of feasibility. And the second answer to this question, if TA is greater than TB, then heat flows from body A to body B. And this third answer to this question, when TA is equal to TB, heat flow stops. Heat flow stops and attains equilibrium. So this is the simplest statement of this second law of thermodynamics in our own language, affirmative sentence. But the scientist very popular in thermodynamics, Clausius made this statement in a more elegant way. This statement is much more, the statement of this Clausius is much more wide. His statement is heat by itself cannot pass from lower temperature to higher temperature. This is the Clausius of statement, very popular statement of this Clausius for this second law of thermodynamics. And this statement is much more wide. As for example, the heat spontaneously can move from higher temperature to lower temperature. Spontaneously, it is a natural process, occurs spontaneously. But if we add some external agency, if we at the cost of this external agency, if we supply the energy from the outside source, then it is possible for the heat to pass from this lower temperature to higher temperature, not by itself, but by the aid of the external agency. As we see, this is the case occurring in refrigerator. Suppose here it is the refrigerator, which is popularly known as the fridge. This is the refrigerator. This is the inside of this refrigerator, and it is at lower temperature, lower T, and suppose it is 0 degrees centigrade. And outside there is atmosphere or the room in which the fridge has been kept, and its temperature is suppose of 40 degrees centigrade. If you keep some amount of water, some amount of water, this water will be converted into ice. The water will be converted into ice, and this heat extracted from this water will be thrown to this atmosphere from the lower temperature to higher temperature. So heat will pass from this lower temperature to higher temperature, not by itself. But here some inside this refrigerator, some machine is there, and this machine is a compressor. This machine is known as compressor, and the compressor is connected to this electrical plug. This compressor takes this electricity from this electrical plug, and this compressor will do this mechanical work. And with this aid of this compressor, it is possible to extract a heat from this lower temperature to this higher temperature. So this Clausius statement is a very popular this type of similar natural processes occurs in different purposes, and we also state this second law of thermodynamics in a different ways depending on the nature of the process. Say a heat, say one water flows from higher level to lower level. This process occurs spontaneously, and this process we can also write in the form of Clausius. Water by itself cannot flow from this lower level to this hard level. Similar other processes are there. Air blows from this higher atmospheric pressure to lower atmospheric pressure, higher barometric pressure to lower barometric pressure. Electricity moves from higher electric potential to lower electric potential. Chemical reaction occurs from this higher chemical potential to lower chemical potential, and so many natural processes are occurring. And all these natural processes have two important criteria. This important criteria is that the criteria one, all these natural processes are spontaneous. Means these processes occurs by itself. No need for any external agency. Spontaneous and thermodynamically irreversible. If we try to reverse this process, which is occurring naturally, we have to supply the energy to reverse this process to this initial state. And the second one, all these natural processes tend to attain equilibrium. Whenever these two bodies are connected, this is TA and this is TB, heat will suppose TA is greater than TB, then heat flows in this place. On the motto, heat flows from A to B with a motto to equalize the temperature of these two bodies. Means two bodies will try to attain the thermal equilibrium. It is not possible that in every case, in every process, it will attain equilibrium, but they will try to attain equilibrium. This is the motto for this natural processes. And now I can give another statement regarding the conversion of heat into mechanical work. You know, the different forms of energy are easily converted into heat energy, but heat has no such a tendency to be converted into other forms of energy. So there is an abundance of heat energy in nature or in this universe. Our aim is to utilize this vast amount of heat energy into mechanical work. And regarding this conversion of heat into mechanical work, the very important statement is the Max Planck and Lord Kelvin. And this statement is known as Planck-Kelvin statement, or in short a PK statement, regarding the conversion of heat into mechanical work. Planck-Kelvin statement. You all know this. Planck is the pioneer of this quantum theory, and this statement again they used a negative sentence. The statement is heat cannot be completely converted into work. Heat cannot be completely converted into work. If it does so, there occurs a permanent change of the working substance. This is the PK statement of this second law of thermodynamics regarding the conversion of heat into mechanical work. So here also it is confirmed that in no way or no contrivance or in no process it is not possible to completely convert heat into mechanical work without suffering some permanent change of this working substance, working system. We can illustrate this one for the conversion of heat into work. Let us illustrate this one by an example. Say here is a cylinder. Here is cylinder containing 1 mole ideal gas. And this is a piston. And this volume V1 and pressure is P1. And in outside it is a vacuum, and this pressure is created by means of this weight, by means of this load over the piston, and pressure is P1 is high. And if we consider a reversible isothermal process containing 1 mole of this ideal gas as the working substance for the conversion of heat into mechanical work, then let us take this cylinder. This is conducting, thermally conducting, perfectly thermally conducting. here is the heat source. Here is the heat source, and the heat source at this temperature T1, at the temperature T. Heat source, and this will supply the heat to this 1 mole of ideal gas, and this its temperature also T, the same temperature. Then how this heat will flow from this to this? If we pick up or if we withdraw the loads over the piston by infinitesimal amount to comply with this process of this reversibility, the piston will move upwards. The piston will also move upwards slightly, and temperature falls. To maintain the temperature T, heat will move from this source, which may be called the reservoir, to this 1 mole ideal gas to keep this temperature fixed. Then again, by installment, if we withdraw the loads from this piston, then this piston will move upwards, and there will be expansion. And suppose this is the final expansion, this is V2, and this one also insulated. Piston is also insulated, so that no heat can escape. Only this one is thermally conducting. And if we apply the first law of thermodynamics, then suppose Q amount of heat flows from the heat source to this ideal gas in order to make this conversion from V1 to V2 in an isothermal process. Then the first law states that, first law of thermodynamics states that Q plus W, suppose this is work done by this gas, by the expansion of this gas, this is W dash, and this one equal to del U, and del U equal to Cv dt for 1 mole of gas, and this one equal to 0, as the temperature is fixed isothermal and the gas is ideal. So Q equal to minus W dash, and this one equal to RT ln V2 by V1, as the process is reversible and isothermal. So this amount of this amount of work is done by the system to the surroundings. And here it is saying that the total heat given to this system is fully or completely converted into mechanical work. But in doing so, the system suffers a permanent change. Piston moves from A to position B, from this position A to position B. And system suffers a permanent change. And the heat engine, which converts this heat into work, heat engine must not be like this. Every heat engine or every engine works in a cyclic process in order to remove this permanent change of this working system. And you know, it is not possible, though heat is completely converted into work, but this system is not acting as the engine. And if this would be so here it is a crank. By crank, here it is a wheel. Whenever it expands, wheel moves. There is a displacement of this wheel, and this system is doing this mechanical work by the movement of this piston, by the movement of this wheel will roll down. Suppose if we ride in a bus and this process occurs, then suppose we are then in this case the length of this cylinder will be so much from the starting point to this arrival point, and this cylinder, length of this cylinder is very, very high. If we like to go from Bankura to Bishnupur, then piston is of length from Bankura to Bishnupur. But every engine works in a cyclic fashion. It comes to this initial state in this second state, and in this case it is a compression. And suppose work is to be required to bring the system back to its initial state, and it is the two-stroke engine actually, one expansion, one compression, and this permanent change of this working system is eliminated. And so in this case of a compression, it will be Q plus W dash. Again it is equal to 0. Suppose the process is reversible, isothermal compression, and this process is isothermal, so CV dt equal to 0, so this is equal to 0. Or you can say Q equal to minus W dash, W double dash is equal to RT ln V1 by V2. As the final volume is V1, initial volume is V2, and so this one. Compress this machine, compress to this initial position, and this permanent change of this working system is wiped out. And this may be act as engine, a two-stroke engine. One is expansion, doing this mechanical work, and in the compression, work is given to this engine to bring back to its initial state. This is one cycle of operation of this engine. And so the total work done by this engine, this one will be equal to W1 plus W2, and this one is actually RT ln V2 by V1 and plus RT ln V1 by V2, and this one is again R2 ln V2 by V1 minus RT ln V2 by V1 by taking this upside down, and this one equal to 0. So by this isothermal reversible process, the engine, this may be taken as this engine working in cycle fashion, cannot produce any work by taking this heat from this source at the same temperature of this engine. If we consider the suppose if we consider the reversible process, reversible isothermal process, in this case also, I have already shown in this reversible cyclic process, heat to be applied from this external source, energy to be applied from this applied source to make this engine come back to its initial state. Means engine cannot produce this positive work to this surrounding, and we like to have this positive work out of this engine. We supply heat and we want this work for our running the machineries. If we use this forward process is reversible and backward process is irreversible, then also I can show that it is not possible to produce, to get this positive amount of work to this surrounding. Suppose this is P and this is V, pressure volume work, and this is the initial state, and this is V1, and this is the final state, and this is V2. And whenever suppose the further process is reversible, so further process is reversible, temperature is fixed, a constant, so this will be the rectangular hyperbola. Here the pressure P1 and volume V1. Here the pressure P2 and volume V2. And the amount of this work is W dash. This amount of this work is W dash, shown by this indicated diagram. And W dash is the work done by the engine or by the system. And if we now reverse this system to bring back to its initial state, then the work will be this one. This will be the W double dash, and this is work done on the system by the surroundings. So in this case also, from this indicator diagram, we can see the W dash is greater than W1. So no net work is done in this way also by the working substance. We are not getting any sort of positive work to this surrounding. So this is why the Clausius makes a very beautiful statement regarding this one. It is impossible to construct an engine, and you know the engine always works in a cycle, working in cycle. Every engine is working in cycle. It is impossible to construct an engine connected to a or connected to a single reservoir. Single reservoir means at this temperature T. Reservoir means this large amount of heat source is being stored within this reservoir, and if any amount of heat is taken out from this reservoir, the temperature of this reservoir will not change. Suppose I can give you allegory that suppose in sea, if you take one bucket of water, then level of this sea will not change, as ocean or the sea contains a vast amount of this water. So it is impossible to construct an engine connected to a single reservoir and which withdraws heat from the source and does positive work to the surrounding. Positive work to the surrounding means it is not possible to construct an engine or any contrivance or any say system working in cyclic fashion that can withdraw the heat from a single reservoir and can produce the positive work to the surrounding. Means we cannot get any sort of positive work from this type of engine or this system if it is connected to a single reservoir. So naturally, the scientists, I have told already, they are very imaginative. When the perpetual motion machine of the first kind fails, as no engine will give you work for indefinite period of time if we do not supply any form of energy to that engine. And that was rejected by the first law of thermodynamics. Then scientists imagined the second way. They tried to construct, they imagined to construct an engine which will take up this heat from these surroundings, as surrounding contains a vast amount of heat energy, and this engine they call perpetual motion machine of the second kind will give us this work for an indefinite period of time, taking the heat from this surrounding at which this engine is working. Then it is possible, if it is possible, then we can run the tram or train by taking this heat from this atmosphere, or we can run this ship taking the heat from this ocean, but it is not possible, it is not found possible. And if it would be possible, then there will be no requirement of this fuel. So this statement of PK second statement, this is the PK second statement, rejected the construction or possibility for constructions of perpetual motion machine of the second kind. So so far we are, as this is the case, but this engine is connected to a single heat source at this temperature T, and T both are same. So the next question comes up, in how we can convert this heat into mechanical work. So long we are giving the negative approach for this conversion of heat into mechanical work. Now we are trying to give you positive statement or requirement for the conversion of heat into mechanical work. And these two requirements are there. Two requirements are there for conversion of heat, into work, heat into work. And the conversion is like that. One criteria or the requirement is that there requires a heat engine. Heat engine is the mechanism or any sort of contrivance. There requires a heat engine for the conversion of of heat into work. And the heat engine must work in cycle. This is very important. Any heat engine must work in cycle. And second, the engine there requires two reservoirs. Two reservoirs. Engine will take heat from high temperature reservoir, say at this temperature T, and it is the heat source. And will convert, the engine will convert a portion of the heat into what? And rest amount of heat is rejected to the lower temperature reservoir. Lower temperature reservoir at the temperature T dash. So these two criteria must be fulfilled for the conversion of heat into work. If we explain this statement in a picturesque way, then this will be the one heat reservoir, say H here, temperature T, and it is called the heat source. It will supply this heat, say this is Q, and here is the engine, and engine is doing this mechanical work. A portion of heat is converted into mechanical work, and this rest heat is Q dash supplies to this LTR, lower temperature reservoir, at this temperature T dash, and it is the heat sink. And reservoir, I told, this is so much amount of heat is stored that if this Q amount of heat is going out from this reservoir, there will be no change of temperature. A finite reservoir also we can consider. Suppose here is the ice, say water, and here it is ice, and its temperature, and here it is vapor. Then if we draw some heat, its temperature is 0 degrees centigrade. If we withdraw the heat from this beaker which contains this water ice at equilibrium along with this vapor, this temperature is called the triple point, and temperature will not change. And if we withdraw the heat from this one, this some water will be converted into ice, the temperature will remain same. If we supply this heat to this system, then also some ice will be converted into water and temperature remains fixed. There will be no change of temperature so long water and ice remaining in equilibrium with its vapor. So this is also, you can say, the finite reservoir. It is finite reservoir. Finite reservoir. So now this is the engine. If we like to consider the efficiency of this engine, then efficiency of this engine denoted by eta equal to the energy output, the energy which we are receiving from this engine, and energy input, the energy given to this engine. And energy output is W and energy input is Q. But the energy balance shows that Q minus Q dash equal to W. So this efficiency will be equal to Q minus Q dash divided by Q, and this one equal to 1 minus Q dash by Q. As there is always an LTR, and LTR will take up some amount of heat, then this one is the positive and fraction. So the efficiency will always be less than 1. No engine we can construct whose efficiency will be equal to 1 or it is less than 100%. It is always less than 100%. We never construct any engine which has the efficiency 100%. If it would occur, then this engine heat is completely converted into mechanical work without suffering any permanent change, and Planck and Kelvin statement fails. Next day, in my next class, I shall consider the Carnot engine, an idealized engine which relates this efficiency with this temperature of the source and sink, 1 minus T dash divided by T. For every engine this efficiency is valid, but only for the Carnot engine this efficiency in terms of temperature will occur, and if we compare this one, then Q dash divided by Q equal to T dash by T. In my next class, I shall discuss the efficiency of this Carnot engine. It is valid for this Carnot engine, and for this Carnot engine, this efficiency we shall derive in my next class. Thank you all who are watching this video. If you like, then please subscribe. Thanks again to you all.